Hello, this is part B of chapter 20, lecture 3 on oxidations of alkenes. So let's continue with examples of oxidation reactions. Here we see 1-methyl 1,2-cyclohexane diol being oxidatively cleaved into 6-oxo-heptanyl. Okay, so we've got 1, 2, 3, 4, 5, 6. So it counts for 6-oxo heptanyl. Okay, this is the ketone side. This is the aldehyde side. And again, per-iodic acid cleaves diols into aldehydes and/or ketones, as you can see on this slide. So let's go to the next slide. Oxidative cleavage of alkenes. Again, as you know, alkenes can be oxidized to 1,2-diols, and 1,2-diols can be further oxidized to aldehydes and ketones, as we have seen just on the previous slide. Also, alkenes can be directly oxidized to carbonyl compounds by ozone and or by potassium permanganate. Here's ozone, O3. In this slide, we see when an alkene is treated with ozone at low temperatures, the double bond breaks. And the carbons that were doubly bonded to each other are now doubly bonded to oxygen. In both cases, doubly bonded to oxygen. This oxidation reaction is called ozonolysis. Ozonolysis. The next couple of slides are on a side topic dealing with chemistry of ozone. So let's take a look. Here's ozone, resonance contributors. Ozone can be produced by passing oxygen gas through an electric discharge. Years ago, old photocopy machines would emit ozone, and you know this because it's an irritant if it's inhaled. This slide shows the structure of ozone as represented by the resonance contributors of ozone. Mechanism for ozonide formation. This is the mechanism of oxidative cleavage of an alkene using ozone. Ozone and the alkene are undergoing a concerted cycloaddition reaction. The oxygen atoms add to the two sp2 carbons in the first step. It is similar to electrophilic addition reactions of alkenes we studied way back in chapter 4. The product is a molozonide or molazonide compound. Molazonide is very unstable because of its two oxygen-oxygen bonds. It quickly rearranges to form a more stable ozonide right here. And here's this very unstable intermediate. Ozonide is explosive and very difficult to isolate. It is also very easily cleaved to carbonyl compounds, as we'll see on the very next slide. As you can see here, ozonide on the left. Of course, its origin was an alkene undergoing oxidation. So ozonide is easily cleaved to carbonyl compounds in the presence of a reducing agent such as zinc or dimethyl sulfide. The products will be ketones, aldehydes, or both. The product is a ketone if the sp2 carbon of the alkene is bonded to two carbon-containing substituents, as on the left. The product will be an aldehyde if at least one of the substituents bonded to the sp2 carbon is a hydrogen, as you can see on the right. The reducing conditions will prevent the aldehydes from being oxidized to carboxylic acids, as it would be under oxidizing conditions, or the presence of hydrogen peroxide. So this slide shows the reduction and oxidation of the ozonide, but overall oxidation of an alkene that is transformed into an ozonide intermediate. Okay, so you can see oxidation occurring here and oxidation. This is oxidation in reducing conditions. We start with so many carbon-oxygen bonds and we end up with so many carbon-oxygen bonds. Down here we have oxidation in oxidizing conditions, reducing, oxidizing conditions. We have to remember that cleaving the ozonide in the presence of zinc or dimethyl sulfide is called working up the ozonide under reducing conditions. Also, we need to remember cleaving the ozonide in the presence of hydrogen peroxide is called working up the ozonide under oxidizing conditions. Okay, let's move on here. Here's an example of oxidative cleavage of an alkene by ozonolysis. The ozonolysis of 3-methyl-2-hexene followed by oxidation by hydrogen peroxide gives propanoic acid and butanone. Here's the propanoic acid and here's butanone. This, of course, is a carboxylic acid. This is the ketone. And we have undergone oxidizing. We've undergone oxidation under oxidizing conditions. So an ozonide is initially formed. In oxidizing conditions, the ozonide forms ketones and or carboxylic acids. Okay. Here are other examples of oxidative cleavage of alkenes in reducing conditions. The ozonolysis of 3-hexene, here at the top, followed by reduction, you can see here, yields 2 moles of propanol. The ozonolysis of 1-methyl-cyclohexene, as you can see here, is followed by reduction, gives 6-ozoheptanol. So we start with 1-methyl-cyclohexene here and 3-hexene, and then under these conditions we result in the products after oxidation. An ozonide is initially formed. In reducing conditions, the ozonide forms ketones and aldehydes, as we can see on this slide. Okay, moving right along. We've been talking about oxidative cleavage of alkenes using ozone. Here is another example, or specific example, but now we're starting with a terminal alkene. Notice the carbon-carbon double bond is on the end of the molecule. We have 1 carbon fragment obtained from the reaction of a terminal alkene with ozone. Terminal alkenes, and we have 1 carbon fragments over here on the right. So 1 pentene and 1 pentene, both, under reducing conditions and under oxidizing conditions in the second steps, will form butanol and aldehyde and formaldehyde. 1 carbon fragment. And here's 1 pentene again, and it's forming butanoic acid under oxidizing conditions and formic acid. So the ozonolysis of 1 pentene followed by reduction, second step, gives butanol and formaldehyde. The ozonolysis of 1 pentene followed by oxidation, the second step, yields butanoic acid and formic acid. So in summary, keep in mind the 1 carbon fragment obtained from the reaction of a terminal alkene with ozone, O3, will be oxidized to formaldehyde if the ozonide is worked up under reducing conditions, and to formic acid if it is worked up under oxidizing conditions. Moving right along, here's ozonolysis involving the benzene ring. The ozonolysis of 1-phenyl-1-butene followed by oxidation, the second step, yields benzoic acid, and propionic acid. So 1-phenyl-1-butene, this is an oxidizing condition, the second step, benzoic acid and propanoic acid. So it's undergone ozonolysis. Cut the molecule in half. Why is the benzene ring not oxidized? Only the side chain, double bond, is oxidized in this example. The stable benzene ring is oxidized only under prolonged exposure to ozone or under very strong oxidizing conditions. Of course, it's very stable. Okay. Interestingly, ozonolysis can be used to determine the structure of an alkene. Chemists have used this, they've turned it around. If you know the structures of the products formed by ozonolysis, you can mentally work backward to deduce the structure of the alkene. Here we've got acetone and butanol. ozolysis products, and working backwards, we can see 2-methyl-2-hexene. This is the alkene that underwent ozolysis to produce these two products. If ozonolysis of an alkene followed by workup under reducing conditions forms acetone and butanol as products, then the alkene was 2-methyl-2-hexene, as you can see here. Okay, let's look at permanganate cleavage of alkenes. Previously, we have seen that alkenes are oxidized to 1,2-diols with potassium permanganate. In the presence of heat, the little triangle there, base or acid, the 1,2-diols will be further oxidized to ketones, carboxylic acids, carboxylic ions, and/or carbon dioxide, as you can see on this slide. So here are 3 different examples of what we're talking about. If the reaction is carried out under basic conditions, as in the top reaction, any carboxylic acid product will be in its basic form. Notice right here, this is the basic form. If the reaction is carried out under acidic conditions, the second reaction here, any carboxylic acid product will be in its acidic form, okay, which is shown here. This is a carboxylic acid in its acidic form. It still has its proton. Up here, it lost its proton. And terminal alkenes form CO2. Here's a terminal alkene, and carbon dioxide is a product. So here is a summary table of the methods used to oxidize an alkene. As you have seen and also you can see in this table, alkenes can be oxidized to epoxides, ketones, aldehydes, carboxylic acids, and carbon dioxide throughout this table. Carbon dioxide if it is a terminal alkene. So we have 7 different reactions shown here. This is peroxy acid up here. And in each of these cases, this is the alkene that gets oxidized. And these are the reagents shown here. And of course, these are all the products. This is a reducing condition. This is oxidizing, obviously, hydrogen peroxide. So if you were to number these, 1, 2, 3, 4, 5, 6, 7. 1, 6, and 7 break only the pi bond of the alkene. Reactions 2, 3, 4, and 5, these right here, these reagents break both the pi bond and the sigma bond of the alkene, resulting in the cleavage of the alkenes. Okay, let's now look at oxidative cleavage of alkynes. The same reagents that oxidize alkenes also oxidize alkynes. They are oxidized to diketones by a basic solution of potassium permanganate at room temperature. They are cleaved by ozolysis to carboxylic acids, as you can see in B, or in the second and third reaction shown here. So we form 2,3-pentadione in the first reaction, acetic acid and propanoic acid in the second, and butanoic acid and carbon dioxide in the second reaction. So ozolysis, which the second and third of alkynes, is followed by hydrolysis in the second reaction, number 2, on each of those cases. It does not require oxidative nor reductive workup like alkenes. Carbon dioxide is obtained from the CH group of a terminal alkyne, as you can see here in the third example. So A, 2-pentyne, is oxidized to 2,3-pentadione with potassium permanganate. In this case, 2-pentyne is oxidized to acetic acid and propanoic acid with ozolysis. And 1-pentene, or rather 1-pentyne, is oxidized to butanoic acid and carbon dioxide with ozolysis. We'll stop right here.